The concept of sleep pressure is central to understanding how caffeine affects alertness and sleep. Throughout the day, the brain gradually accumulates a molecule called adenosine, which functions as a homeostatic regulator of wakefulness. Adenosine is produced as a byproduct of cellular metabolism, particularly from the breakdown of ATP, the energy currency of the cell. As adenosine levels rise in the brain, it binds to specific receptors located on neurons, signaling that the body has been awake for an extended period. This signal produces the sensation of sleepiness and gradually increases the drive to sleep, preparing the nervous system to transition from wakefulness to rest. The longer a person remains awake, the higher the concentration of adenosine and the stronger the pressure to sleep becomes, creating a natural balance between wakefulness and restorative sleep. Caffeine, the primary active component of coffee and many other beverages, exerts its stimulating effects primarily by targeting this adenosine system. Rather than reducing the production of adenosine, caffeine acts as a competitive antagonist at adenosine receptors. This means that caffeine molecules occupy the receptor sites where adenosine would normally bind, effectively blocking the chemical signal that induces sleepiness. When caffeine is present, the brain continues to function as if adenosine levels are low despite the ongoing accumulation of adenosine. This is why people feel alert and mentally focused after consuming coffee. The nervous system is temporarily prevented from registering the natural biochemical signals that signal fatigue. The impact of caffeine on sleep pressure is not merely a short-term effect. While caffeine blocks adenosine receptors and temporarily masks feelings of tiredness, it does not remove adenosine from the system. Consequently, the underlying sleep pressure continues to build in the background even while the individual feels awake and alert. Once the effects of caffeine begin to diminish, all of the accumulated adenosine can bind to receptors at once, often resulting in a sudden and pronounced sense of fatigue, commonly referred to as a caffeine crash. This delayed impact highlights the distinction between perceived alertness and the body's actual need for sleep, emphasizing that caffeine temporarily overrides the brain's natural signaling without eliminating the physiological requirements for rest. The way caffeine interacts with adenosine receptors also varies depending on individual differences in sensitivity and metabolism. Genetic factors influence the expression and function of enzymes in the liver that break down caffeine, as well as variations in adenosine receptor density and activity in the brain. Some individuals metabolize caffeine quickly, reducing the duration of receptor blockade and minimizing sleep disruption. Others metabolize caffeine more slowly, extending the period during which adenosine receptors remain occupied and increasing the potential for interference with natural sleep onset. This variability explains why the same cup of coffee can produce alertness in one person, while causing significant difficulty falling asleep in another. Moreover, the accumulation of adenosine throughout the day is not uniform across brain regions. Areas of the brain involved in executive function, attention, and alertness, such as the prefrontal cortex, are particularly sensitive to adenosine signaling. By blocking receptors in these regions, caffeine can disproportionately enhance cognitive performance and reduce the subjective experience of tiredness. However, other brain regions, such as the hypothalamus, which regulates circadian rhythms and sleep-wake cycles, continue to experience the effects of adenosine accumulation. This regional variation contributes to the complexity of caffeine's effects, as the body may be physiologically ready for sleep, even while certain areas of the brain remain highly active. Timing of caffeine intake significantly influences its interaction with sleep pressure. Consuming caffeine early in the day allows the body sufficient time to metabolize it before the natural rise in sleep pressure during the evening. In contrast, consuming caffeine in the afternoon or evening can block adenosine receptors during a period when sleep pressure is peaking, making it more difficult to initiate sleep. Because adenosine continues to accumulate even during caffeine's receptor blockade, the later caffeine is consumed, the more pronounced the interference with the natural transition from wakefulness to sleep, potentially reducing both sleep duration and quality. Another critical factor in understanding how caffeine affects sleep is its half-life, which determines how long caffeine remains active in the body. The half-life of a substance refers to the amount of time required for the body to eliminate half of the consumed compound. For caffeine, the average half-life is approximately 5 to 6 hours, although this can vary significantly depending on individual factors such as age, genetics, liver function, and hormonal status. Because caffeine has a relatively long half-life, a substantial portion of the substance may still be circulating in the bloodstream many hours after consumption. continuing to block adenosine receptors and sustain alertness well into the evening. The liver plays a central role in metabolizing caffeine through a set of specialized enzymes, primarily cytochrome P450-1A2. These enzymes break down caffeine into metabolites that can be more easily excreted by the kidneys. However, the efficiency of this metabolic process differs between individuals. Genetic differences in the CYP1A2 enzyme mean that some people metabolize caffeine rapidly, clearing it from the body more quickly and experiencing shorter-lasting effects. Others metabolize caffeine more slowly, which prolongs the duration of receptor blockade and increases the likelihood that residual caffeine will interfere with sleep onset and quality, even if the initial dose was consumed hours earlier. The half-life of caffeine also means that repeated consumption throughout the day can lead to cumulative effects. Each subsequent cup of coffee, tea, or other caffeinated beverage adds to the total amount of caffeine in the system, extending the period during which adenosine receptors remain blocked. For example, someone who drinks multiple cups of coffee between morning and late afternoon may have significant levels of caffeine circulating in their bloodstream late into the evening. Even if they feel tired, the remaining caffeine can delay the body's ability to transition into sleep, creating a mismatch between subjective sleepiness and physiological sleep pressure. Because caffeine's half-life overlaps with the natural increase of sleep pressure in the evening, the timing of consumption is particularly important. Consuming caffeine within 8 to 10 hours of bedtime is often sufficient to interfere with the initiation of sleep. The longer caffeine remains in circulation, the greater the likelihood that it will reduce both the quantity and quality of sleep. Even low residual concentrations of caffeine can alter the depth of restorative sleep stages, such as slow-wave sleep, and increase the frequency of nighttime awakenings, leaving individuals feeling less rested despite spending sufficient time in bed. Hormonal and physiological states can further influence caffeine metabolism and its half-life. For example, pregnancy slows caffeine metabolism due to hormonal changes, meaning that caffeine can remain active for longer periods. Certain medications that affect liver enzymes can also alter the rate at which caffeine is cleared from the body. Additionally, factors like age and liver health play a role. Older individuals, or those with impaired liver function, may experience prolonged caffeine activity, increasing the potential for sleep disruption even with moderate consumption earlier in the day. Understanding caffeine's half-life also helps explain why the perceived alertness it produces can persist beyond the expected period. While individuals may notice an immediate boost in energy and focus after consuming caffeine, the substance continues to exert subtle effects as it slowly metabolizes. Adenosine receptors may remain partially blocked, reducing the ability to feel natural sleepiness even as the circadian system signals that the body is preparing for rest. This interaction illustrates why late-day caffeine consumption can delay sleep onset, fragment sleep cycles, and reduce the overall restorative quality of sleep. Because of these pharmacokinetic properties, managing caffeine intake requires not only consideration of dose but also timing. The total amount consumed, the rate at which an individual metabolizes caffeine, and the proximity to bedtime all determine the degree to which caffeine will interfere with sleep. Even for those who do not feel overly stimulated, residual caffeine in the bloodstream may subtly alter sleep architecture, reducing deep sleep and REM sleep stages that are essential for recovery, learning, and overall health. Caffeine affects not only the ability to fall asleep, but also the architecture of sleep itself, which refers to the structure and pattern of different sleep stages throughout the night. Sleep is composed of cycles that alternate between non-rapid eye movement, NREM sleep, and rapid eye movement, REM sleep. NREM sleep is further divided into stages, with slow-wave sleep, SWS, also known as deep sleep, being the most restorative phase. During deep sleep, the brain engages in processes essential for physical recovery, immune system support, and memory consolidation. REM sleep, on the other hand, is critical for cognitive functions, emotional regulation, and learning. Caffeine consumption can alter both the duration and quality of these sleep stages, leading to reduced restorative benefits even if total sleep time is not drastically shortened. The primary way caffeine impacts sleep architecture is through its antagonism of adenosine receptors. Adenosine accumulation naturally promotes sleep pressure and facilitates the transition into deep sleep stages. By blocking these receptors, caffeine not only delays the onset of sleep, but also reduces the body's ability to enter and maintain deep sleep. Research has consistently shown that caffeine can decrease the proportion of slow-wave sleep, resulting in lighter and less restorative sleep cycles. As deep sleep diminishes, The physiological processes that depend on this stage, such as tissue repair, immune function, and the clearance of metabolic waste from the brain, are compromised. In addition to reducing slow-wave sleep, caffeine can also fragment sleep, increasing the frequency of nighttime awakenings. Even small amounts of residual caffeine circulating in the bloodstream can heighten neural activity in regions of the brain associated with arousal, making it more difficult for the nervous system to maintain continuous sleep. This fragmentation not only interrupts the progression through normal sleep cycles, but can also lead to a perception of poor sleep quality, causing individuals to feel less rested upon waking. Over time, repeated disruptions in sleep architecture can accumulate, contributing to chronic sleep deficits and reduced overall health. Caffeine also influences REM sleep, the stage associated with dreaming, emotional regulation, and memory processing. By delaying sleep onset and reducing the depth of NREM sleep, caffeine can indirectly shorten REM periods or alter their timing within the sleep cycle. REM sleep tends to occur in longer stretches during the later part of the night, so if caffeine delays the transition from wakefulness to sleep, the total duration of REM sleep may be compressed. This can affect cognitive performance, mood stability, and the ability to consolidate learning from the day, highlighting that the effects of caffeine extend beyond simple sleep latency. Individual sensitivity to caffeine plays a significant role in how sleep architecture is affected. People with slower caffeine metabolism experience prolonged receptor blockade, which increases the likelihood of deep sleep reduction and sleep fragmentation. Genetic factors, age, liver function, and even hormonal fluctuations can influence how quickly caffeine is cleared from the system, making some individuals more susceptible to disruptions in sleep cycles. These differences explain why two people consuming the same amount of caffeine may experience vastly different impacts on their sleep quality. The timing and quantity of caffeine consumption are critical in determining its effects on sleep architecture. Morning consumption may have minimal impact on nighttime sleep for many individuals, as the body has sufficient time to metabolize the compound before the evening. In contrast, consuming caffeine in the late afternoon or evening can interfere with the natural buildup of sleep pressure and delay entry into deep NREM and REM stages. Even moderate doses consumed later in the day can reduce restorative sleep, emphasizing the importance of aligning caffeine intake with the body's natural circadian rhythms. Caffeine's effects on sleep architecture illustrate that the compound does more than temporarily increase alertness. It fundamentally alters the biological processes that underpin restorative sleep. By reducing deep sleep, fragmenting cycles, and potentially shortening REM stages, caffeine can limit the physiological and cognitive benefits normally gained from a full night of rest. These changes highlight the need to consider both the amount and timing of caffeine consumption to maintain optimal sleep quality and overall health. Caffeine's effects on alertness and sleep are not limited to adenosine receptor blockade. It also exerts a significant influence on other neurochemical systems that regulate arousal, attention, and motivation. By affecting neurotransmitters such as dopamine and norepinephrine, caffeine enhances brain activity in regions responsible for wakefulness, cognitive performance, and mood, which contributes to the feeling of heightened alertness after consumption. While this stimulation is often sought for increased focus and productivity, it also creates a state in the nervous system that can conflict with the natural processes required for sleep, particularly when caffeine is consumed later in the day. Dopamine, often referred to as the brain's reward neurotransmitter, plays a critical role in motivation, attention, and executive function. Caffeine indirectly increases dopaminergic signaling by blocking adenosine receptors that normally inhibit dopamine activity. By reducing this inhibitory influence, caffeine enhances dopamine availability in key regions such as the prefrontal cortex and striatum. This increase in dopaminergic activity improves cognitive performance, reaction times, and the perception of energy. However, heightened dopamine activity also promotes neural arousal, which can make it more difficult for the brain to transition from a state of wakeful alertness to the slower, synchronized neural activity required for sleep onset. Norepinephrine, another neurotransmitter affected by caffeine, is involved in the body's fight-or-flight response and general arousal systems. It regulates attention, vigilance, and the ability to respond to external stimuli. Caffeine stimulates norepinephrine release indirectly through its effects on adenosine receptors in the central nervous system. Elevated norepinephrine increases heart rate, blood pressure, and overall neural activation, supporting wakefulness and alertness. While these effects are beneficial for short-term cognitive performance, They also maintain the brain in a physiologically activated state that is less compatible with the gradual downregulation of neural activity that normally precedes sleep. This neurochemical stimulation can delay sleep onset and contribute to lighter, less restorative sleep stages. The combined influence of dopamine and norepinephrine means that caffeine does more than simply mask sleep pressure. It actively changes the balance of excitation and inhibition in neural circuits. Normally, as the day progresses, adenosine accumulation and circadian signals reduce overall neural excitation, allowing sleep-promoting networks to dominate. When caffeine is present, these networks remain partially inhibited, and excitatory systems continue to drive alertness. This shift in neural dynamics can create a mismatch between subjective feelings of wakefulness and the physiological need for sleep, making it more difficult to fall asleep and achieve deep restorative stages of sleep. Caffeine's neurochemical effects also extend to brain regions involved in attention, memory, and executive function, such as the prefrontal cortex and hippocampus. By enhancing neurotransmitter signaling in these areas, caffeine improves cognitive performance, focus, and short-term memory. However, during the transition to sleep, these same regions require reduced excitatory input to allow the slow-wave oscillations characteristic of deep NREM sleep. Elevated neurotransmitter activity from caffeine can interfere with this transition, reducing the proportion of slow-wave sleep and impairing the restorative processes that occur during the night. Individual differences further modulate the neurochemical impact of caffeine. Genetic variations influence both the density of adenosine receptors and the responsiveness of dopaminergic and noradrenergic systems. People with higher receptor sensitivity or slower caffeine metabolism may experience stronger arousal effects, which can exacerbate difficulties with sleep onset and quality. Additionally, lifestyle factors such as stress, diet, and prior sleep debt interact with caffeine's neurochemical effects, potentially amplifying or diminishing its impact on alertness and sleep. Because of caffeine's stimulation of dopamine and norepinephrine pathways, the timing of consumption is critical. Early morning intake aligns with naturally rising circadian alertness and may enhance cognitive performance without substantially interfering with nighttime sleep. Conversely, afternoon or evening consumption maintains elevated neural activity during a period when the brain is biologically preparing to reduce arousal. Even moderate levels of caffeine during these hours can prevent the nervous system from entering the quiet, regulated state necessary for deep sleep, thereby reducing overall sleep quality and the restorative benefits of a full night's rest. Caffeine can also affect sleep by interfering with the body's circadian rhythm, the internal biological clock that regulates patterns of alertness and rest over a roughly 24-hour cycle. The circadian rhythm is controlled by a region of the brain called the suprachiasmatic nucleus, which is located in the hypothalamus and responds primarily to light cues from the environment. This clock signals the release of hormones such as melatonin, which promotes sleep onset in the evening, and cortisol, which supports alertness in the morning. Under normal conditions, the circadian rhythm works in concert with sleep pressure, the gradual accumulation of adenosine throughout the day, to ensure that the timing of sleep aligns with the body's internal signals. When caffeine is consumed, particularly in the afternoon or evening, it can disrupt this coordination between circadian signals and sleep pressure, delaying the initiation of sleep and altering sleep patterns. One of the key ways caffeine interacts with the circadian system is through its effect on adenosine receptors, which play a role not only in promoting sleep pressure, but also in modulating circadian signaling pathways. Adenosine accumulation during the day helps the body gradually transition into a state that favors sleep at night. By blocking these receptors, caffeine delays this transition, effectively telling the brain that it is not yet time to sleep. This delay can conflict with the natural circadian signals that are simultaneously preparing the body for rest. As a result, individuals may feel alert even when the body is biologically ready for sleep, which can lead to difficulty falling asleep and misalignment of sleep timing. The timing of caffeine consumption relative to the circadian cycle is therefore critical. Morning caffeine intake generally aligns well with the circadian rise in alertness and does not significantly interfere with nighttime sleep. However, consuming caffeine in the late afternoon or evening can extend alertness into a period when circadian-driven signals are promoting sleep. This misalignment can lead to delayed sleep onset, shorter total sleep duration, and increased difficulty achieving restorative stages of sleep, such as slow wave and REM sleep. For many individuals, even moderate caffeine intake several hours before bedtime is enough to disrupt the natural coordination between sleep pressure and circadian signaling. Caffeine can also interact with circadian regulation indirectly through its impact on neurochemical systems that modulate alertness. By increasing dopaminergic and noradrenergic activity, caffeine elevates arousal levels, which can further counteract circadian-driven signals for sleep. The nervous system may remain in a heightened state of alertness despite the circadian clock signaling that it is time to wind down. This interaction can result in a disconnect between the subjective feeling of alertness and the physiological need for sleep, exacerbating difficulties in initiating sleep and reducing overall sleep quality. Individual differences play an important role in how caffeine affects circadian timing. Genetic variations in enzymes that metabolize caffeine and an adenosine receptor sensitivity influence the duration and intensity of caffeine's effects on the brain. People who metabolize caffeine more slowly may experience prolonged disruption of circadian-aligned sleep signals, while those with faster metabolism may be less affected. Lifestyle factors such as exposure to artificial light, irregular sleep schedules, and prior sleep deprivation can also interact with caffeine's circadian effects, amplifying or mitigating its impact. Understanding the interaction between caffeine and circadian rhythms highlights the importance of strategic timing for consumption. Early-day caffeine can enhance alertness without interfering with circadian-driven sleep signals, while late-day intake can misalign internal biological clocks and delay sleep onset. This disruption is not limited to sleep duration. It can also affect sleep architecture, reducing deep and REM sleep, and impairing the restorative functions of the night. Over time, repeated circadian misalignment caused by caffeine can contribute to chronic sleep deficits, daytime fatigue, and negative impacts on cognitive performance and overall health. Another significant factor in how caffeine affects sleep is individual sensitivity and cumulative intake. People vary widely in how their bodies respond to caffeine, both in terms of metabolism and neural effects. Genetic differences play a major role in determining sensitivity. Variants in the CYP1A2 gene, which encodes a liver enzyme responsible for metabolizing caffeine, influence whether an individual breaks down caffeine quickly or slowly. Those with slower metabolism experience prolonged effects, as caffeine remains active in their system for a longer period, maintaining adenosine receptor blockade and heightened neural activity. Conversely, fast metabolizers may process caffeine rapidly, experiencing less interference with sleep, even if intake is moderate. These genetic differences mean that the same dose of caffeine can have dramatically different effects on alertness, sleep onset, and sleep quality from one person to another. In addition to genetic factors, habitual caffeine consumption shapes sensitivity over time. Regular consumers often develop partial tolerance to some of caffeine's effects, particularly those related to subjective alertness and cardiovascular stimulation. However, tolerance does not completely prevent interference with sleep. Even habitual users may experience delayed sleep onset, reduced deep sleep, and fragmentation of sleep cycles if caffeine is consumed late in the day. This demonstrates that tolerance can reduce the perceived intensity of caffeine's stimulating effects without eliminating its impact on the biological processes that regulate sleep. Cumulative intake also plays a critical role in how caffeine affects sleep. People often consume caffeine in multiple forms throughout the day, including coffee, tea, soft drinks, energy beverages, chocolate, and certain medications. Each source adds to the total amount of caffeine in the body, increasing the likelihood that significant levels will persist into the evening hours. Even moderate afternoon consumption, when combined with morning caffeine, can maintain enough circulating caffeine to disrupt sleep pressure and delay melatonin release, particularly in slow metabolizers. Awareness of total daily caffeine intake is therefore essential for understanding potential sleep disruption. The timing of caffeine intake is especially important in relation to its cumulative effects. Early morning consumption typically coincides with the natural circadian increase in alertness, which minimizes sleep interference while supporting daytime cognitive performance. Afternoon and evening intake, however, coincides with the period when the circadian system signals the body to prepare for sleep. When caffeine remains active during this time, adenosine receptor blockade, heightened dopamine and norepinephrine activity, and increased arousal can combine to significantly delay sleep onset. This can result not only in shorter sleep duration, but also in poorer sleep quality, as deep and REM sleep may be reduced or fragmented. Lifestyle factors further influence sensitivity to caffeine's effects. Stress, Prior sleep debt and irregular sleep schedules can exacerbate caffeine-related sleep disruption. For instance, someone who is already sleep-deprived may consume caffeine to compensate, but the lingering effects may delay restorative sleep later, creating a cycle of dependency and disrupted sleep architecture. Conversely, good sleep hygiene and consistent sleep schedules can mitigate some of caffeine's negative effects, although timing and dose remain key variables. Understanding individual sensitivity and cumulative intake highlights the importance of self-awareness and strategic caffeine use. People who are particularly sensitive may need to avoid caffeine entirely after mid-morning, while others with faster metabolism may tolerate moderate afternoon intake. Tracking all sources of caffeine throughout the day can help individuals align consumption with circadian and sleep pressure rhythms. By considering genetics, habitual use, cumulative intake, and timing, people can maximize the alertness benefits of caffeine while minimizing its disruptive effects on sleep quality and overall restorative processes. When all these factors, genetic variability, habitual tolerance, cumulative intake, timing, and lifestyle influences, are considered together, it becomes clear that caffeine's impact on sleep is highly individualized. Even moderate consumption can interfere with the natural buildup of sleep pressure, delay sleep onset, and reduce the restorative quality of deep and REM sleep in sensitive individuals or those who consume caffeine later in the day. By understanding their personal sensitivity, monitoring total caffeine intake from all sources, and strategically timing consumption to align with natural circadian and sleep pressure rhythms, individuals can harness the alertness and cognitive benefits of caffeine while minimizing its disruptive effects on sleep. Careful management of caffeine intake allows people to enjoy both improved daytime performance and high-quality restorative sleep.